Yes, so here's the topic of my talk, and here's an outline, and the main object of study here would be planar curves and Gauss diagrams, the objects which comes from topology and the combinatorial approach to topology. So let me start with this object straight away. So what we are interested in a planar curves object you will see on the left of the screen now, and their combinatorial presentations B and C you see in the center and on the right of the screen. So how do we get a Gauss diagram? This is an object in the middle from the planar curve. It's very simple procedure. You just start from any point and traverse a curve. And in parallel, you traverse a circle. And once you hit a crossing point, you put a point on the circle. And once you do the full traversal, you will get a circle with the points in there. And then you connect the points which correspond to the same crossing. So in this case, if I start from somewhere before crossing 1 and go to the clockwise, I will get a Gauss diagram which will look like that. And now we may consider now it's not as a continuous object, but rather as a graph. And that we will call Gauss or chord diagram. And now in the third object, you see now on the screen, it's an interlacement graph. Interlacement graph is a structure which could be obtained from a Gauss diagram by very simple procedure. To each chord here in Gauss diagram, you associate a vertex. And now you connect the vertices if and only if corresponding chords are intersecting. So it's easy to see that if I apply this procedure, I will get C from B just straight away, very simple to see. And another thing you can notice that immediately we will get to point 3, which is disconnected from the rest of the graph. So graph is disconnected, and that corresponds, so to speak, a lone chord, which you will see 3, 3 shown in a picture in the middle. So these are our objects of study here. Now, a few more definitions before we proceed. First of all, we will be interested mostly in prime diagrams. These diagrams in terms of interlacement graph means that the graph is connected. So there are no lone chords somewhere in the diagram. And we also would be interested in equivalence on these diagrams, and it could be defined in a variety of ways, but a simple and straightforward way. If the two diagrams are equivalent, if they're diagram graphs, it means not interlacement graph like that, but diagram graphs in the middle are isomorphic. So that's all we need to proceed it further. And now we'll return back more than 200 years ago to the classical question, which was posed by Carl Gauss, who asked, if you start with a chord diagram, object in the middle of my screen, can you actually get back and draw a planar curve if there exists a planar curve for which this chord diagram would be an encoding? So can it be obtained from a planar curves? And he proposed already then, around 1800, that any chord diagram should intersect even number of other chords. In terms of interlacement graph, it means every vertex should have even degree in this graph. Easy to see, so if it's violated, you cannot embed this curve into the plane. But it took more than 100 years actually to formulate full realizability criteria. That was only a necessary condition, but not sufficient. And it was done by Dehn in the 1930s. And since then, many variants of this criteria have appeared in different terms, both geometrical or topological, or more algebraic or combinatorial form. But important point for today's presentation is that this realizability criteria can be formulated in terms of interlacement graphs only. Let me quickly go back. So it means in order to answer whether this is possible, B transformed to A, central to the left picture, it's enough to consider only information on the right in this interlacement graph. That's enough to answer this question, positively or negatively. Now, and here you see one of the first such conditions explicitly formulated, or such criteria, which first one is just a Gauss condition, and second one, which is saying something about subset of vertices in a graph. So there is a such subset such that some clearly formulated condition you see now on the screen, I won't read it, something in terms of just neighboring and odd even numbers of neighbors of one kind or another kind. So it's very simple, but from computational perspective, as well as from definability perspective, subset, dealing with subsets, you're actually dealing with second order constraints. So that's kind of quite complex in many different senses of this word. Now we quickly go back to the almost modern time, 3 years ago, 2 years ago. There are new variants of these conditions formulated in the work by Grinblat and Lopatkin and also by Biryukov. And the conditions are pretty simple. So let me start with this PC2 from Grinblat Lopatkin. So essentially, it says each pair of neighboring vertices has an even number of common neighbors. Very simple condition. And second condition, they formulated in terms of transformed graph. So they claim it has to satisfy the same condition if you transform a little bit a graph, reduce a graph. So essentially, this operation is some local inversion. I won't go into details because I would be mostly dealing with a variant which Biryukov formulated 2019. And by the way, this variant already appeared in a paper by Grinblat Lopatkin, but it was presented for another cause in their paper. So this condition is actually very simple because it says something about triple of nodes in a graph, which satisfies some connectedness condition and also some parity condition. So the number of vertices with specific property should be even. And property itself is very simple. You see it on the screen. So what we can conclude out of this, and that was actually our starting point for the whole research reported here. We were very much surprised. I personally was very much surprised because now these conditions, be it Grinblat Lopatkin variant or Biryukov variant, are very simple. There is no second order quantification. There is nothing like a transitive closure, a bit more expensive operation to deal with, to define that. Everything formulated essentially in terms of first order logic, plus a little bit of more, and that is a parity quantifier. So you need to be able to express parity condition, to say some number are odd or even. And that's opened a route for experimental investigation of these conditions, and in particular for enumeration of various classes of such diagrams from, say, purely mathematical perspective. So that was our starting point. Now, it was clear from the beginning that such simply formulated conditions you may almost directly, I mean, just very straightforward way to translate into some ready-to-go constraint solvers. And that's what we did. And here you see just the variants of these conditions. And in fact, this is a Biryukov variant. All essential conditions you need to formulate as a constraints for the graph, so that now you can run a constraint solver and receive and to get some solutions. And just in order to give some flavor what we are talking about in terms of efficiency, here I've just collected a small sample of data. So this is a time to generate all possible solutions for such system of constraints, which for the size of a diagram 6, 7, 8, and 9. So you see that grows quite fast, in fact, exponentially. So it's maybe not kind of realistic, but here the difficulty is in the size of these sets. The number of the solution also grows very fast. And also these times are reported already for some optimization in terms of we inserted some simple symmetry breaking condition as well, but not full account of, say, non-isomorphic solution, no equivalent solution. So that is was a starting point to use the plain constraint solving. We also experimented with the same MiniZinc solver, directly express conditions on diagrams, not just on interlacement graph, but on diagrams. There is much more diagrams than corresponding interlacement graph. And we use so-called even odd matching encoding, which I hope to will explain just in a few minutes time. But let me complete first about this MiniZinc direct approach. So it might be feasible to generate examples of such diagrams, especially if you are interested in diagrams with additional properties. So it might be a very reasonable approach. But since we were interested in enumerating non-equivalent ones, the approach taken is that you generate all solutions and then filter them by, say, non-isomorphism checking or equivalence checking. And it's become unfeasible even for rather moderate sizes. Too many equivalent and isomorphic solutions. So that was a challenge. And since we still would like to apply these very nice conditions by Grinblat, Lopatkin, and Biryukov, we designed a different approach, alternative approach, which also has a roots in constraint satisfaction, but it's allow you to do more processing on the fly, not to generate all solutions and then filter out non-interesting one, but you would rather to do it on the fly. And how it happens? Well, just you see it on the screen, generate a candidate solution, test if it satisfies criteria, and check also if you have already seen equivalent one. And if yes, if it passes through these checks, then store a new solution and repeat until you exhaust all possible candidates. And we implemented this strategy in SVI Prolog as an algorithm suite. And now let me show you some also interesting, nice mathematical statements which rely on these algorithms for diagram generation. So we implemented two algorithms. The first one is direct and second is incremental. And direct algorithm is based on what I already named as an even odd matching. So what it is even odd matching? Okay, so you have a diagram here on the picture. It has 9 chords or 18 ends of the chords. Now, how you can encode all essential information? It's very simple. You just store the pairs. Numbers, it's numbered all points clockwise from 0 to 17. So you store 0 and 5, that information about this chord, then 1 and 8, 2 and 9, and so on and so forth. So in this way, you split the set from 0 to 17 into 2-element subsets. But each element in this subset, one element would be even and one element would be odd, since the name, even odd matching. So that is a data structure to keep information about Gauss diagrams. Now, but how do you generate such even odd matching? And here is our small discovery. Well, it's turned out to be known almost a folklore statement, but discovery is that there is a very simple bijection between symmetry group Sn and the set of such a even odd matching on the elements from 0 to n minus 1. And if you've never seen it before, I would encourage you to try and invent your own, but here is just a formula. But in fact, there is much more beauty behind this formula, which I don't explain, but just trust me, this is the bijection, very simple. So how do we generate diagrams? Now we generate first permutations by each of the known algorithms. You generate permutation, then apply this bijection. By applying this bijection, you receive some already even odd matching, but then you need to produce a canonical form, because among several even odd matching, you would have you may have equivalent ones. So you must kind of to reduce them to some canonical form, and that is also implemented in a I would say more or less straightforward moment. There is no too deep mathematics behind. It's just to canonize more or less it's very natural way, and then effectively you test produced even odd matching or Gauss diagram for the conditions you are interested in. So this algorithm is also parameterized by a set of properties which may be embedded in the algorithm. So you generate it on the fly, test the properties, and store the results. Very simple, and it goes like that. Now, we also produced more interesting algorithms. In my personal perspective, it's a bit more interesting. It's not so direct. And instead of generating all diagrams of a given site from scratch, it generates a set of diagrams based on a size n-1. So if you already generated smaller sizes, now you can produce bigger sizes. And how do you produce it? By this very simple move. So essentially all you need diagrammatically is just to take a diagram of a smaller size in which chords are located as shown on this picture, and then to remove this dotted chord here and insert 2 new chords on the right. So you increase the size of a diagram by one more chord. But the point is, if you do it for all possible diagrams of a smaller size, and then you generate all possible diagrams of a bigger size, except one special diagram, which essentially is called a wheel, which essentially means a diagram in which dots are kind of opposite dots on a circle are connected, exactly opposite. So this diagram cannot be obtained by this procedure. It has to be added after you generate all this. So we implemented this algorithm as well, and it has turned out to be much well, essentially more efficient. So it's allowed us to treat diagrams of sizes by 2 more instead of 11, which was a maximum, up to 13, size of 13 by using this algorithm. Some remarks on implementation. So as I said, we implemented in a SWI Prolog, logic programming language, but graph isomorphism, which we used in a part of our experiments, was implemented separately in a Python using this library, quite well-known library for graph isomorphism. Now, let me go to the results then. So what we can get out of it? Of course, you can experiment, you generate different diagrams, but that was our first very surprising discovery, that once you generated all diagrams satisfying Biryukov condition and Grinblat Lopatkin conditions, this B and GL, 2 lower lines in these tables, we discovered that number of diagrams which satisfy this condition is different from a numbers of diagrams which are realizable, which is well known and well tabulated. There are several algorithms already checked and tested and verified. So we would find the differences will start at the size 9. While there is 101 realizable diagrams, number of diagrams satisfying B or GL conditions are 102. So we spent a couple of weeks finding this different. And here is well, first is a conclusion that these conditions were published in a journal, well-established journal of knot theory and ramifications. And it was interesting, and we couldn't believe at first that indeed we found a mistake in the main theorems of both papers, but this indeed turned out to be the case, and the authors has confirmed that indeed that is an error in their papers. And here is the smallest counterexample we found by using this approach. So what it is, this is a diagram which satisfies both B and GL conditions, but is not realizable. It can be tested by many possible ways. First, I have tested personally manually using one of the classical algorithms. Now you see these counter examples for size 10, and we enumerated all these counter examples, I believe, up to the size 12. And it also grows very fast. Okay, so that was one of the outcomes of this work. Now, once we have this tool, now we can enumerate various classes of Gauss diagrams. And so we enumerated all prime Gauss diagrams, and we also enumerated all prime and non-prime without imposing any realizability conditions. And some of these numbers were known in the literature and confirmed by us and extended. Some of these numbers were not known, and this constitute a new contribution in experimental enumerative combinatorics, if I may say so. Now, what else? We also enumerated these interlacement graphs. That's the interesting structure. This is more compact and it contains all essential information. And it seems nobody bothered before this research started to actually enumerate and see what are the examples of these graphs. And so that was contributed as a new sequence to this online encyclopedia of integer sequences. We also established some connection with alternating nodes. So these numbers of these graphs has turned out to be close, but not quite the same as the sequence for numbers of so-called alternating nodes in knot theory. But we clarified all the relationships, and the details can be found in the archive paper. I will give a reference. So now I am arriving almost at the end of my talk, just to say, okay, so there is obviously ongoing work, new experiments, and we are doing some improvement of existing implementation, especially in a better integration of graph isomorphism testing. As I said, at the moment it's implemented separately. So we generate all diagrams, we filter them to some extent, but then we pass it to the correct graph isomorphism procedure implemented elsewhere. So better integration is needed. Now, another very promising approach, but with also now with very clear obstacles, is that Gauss realizability with a SAT solving. SAT solving brings, of course, efficiency, but if you are mostly interested in enumeration, then there is this problem how to formulate correct symmetry breaking conditions. Of course, you can insert some symmetry breaking conditions, but they normally wouldn't account for the whole, say, isomorphism checks or equivalence checks in terms of Gauss diagrams. So that is still an interesting challenge. And also a very interesting approach would be to apply quantified SAT, because in quantified SAT, you can encode directly Rosen-Tichel solutions, conditions, second order conditions. And then, so kind of local and modest goal here, at least to receive confirmation of how this results by direct use of QSAT in terms of demonstrating concrete counterexamples for the Biryukov conditions and Grinblat Lopatkin conditions. And finally, let me finish by some conjecture. Because attractive point of these new conditions was they're very simple. So essentially first order logic plus parity, all what is needed. And it's turned out they're wrong. And the conjecture in which we are pretty sure is that Gauss realizability is not expressible by this means. So you still need either second order quantifier or some variant of transitive closure or fixed point construction. So you cannot do it that simple, just local properties and some parity around it. Okay, so we arrived at the conclusion. So we demonstrated experimental approach, which uses constraint satisfaction and related techniques. From viewpoint of mathematical applications, well, you see it here, validation of some statements, invalidation, new enumeration results, and cross-validation and explanation of known enumerations. But also it gives a very good field to explore various constraint satisfaction techniques and their variants and related techniques in order to do efficient explorations of solutions, efficient exploration of such structures. Here are some references, and most of it is available in these two archive papers, if you're interested in further details. And at this point, let me finish my talk, and thank you very much for your attention.
Thank you much indeed for that, Alexei. Very interesting talk, and it's good to see the importance of experimental verification, as you've shown. So we've got time for some questions. While we're waiting, could you perhaps go back a slide and show us the references?
Yes.
Thank you. I didn't get them down. Yes.
Yeah, by the references, I also would notice that the last one, it's already written in collaboration with the author of one of these papers, which we invalidated the result. So the author was very, very keen to collaborate, and we fixed the error. But to some extent, unfortunately, it remains outside of this simple expressible class. You still need some form of transitive closure. Oh, yes, I see. Yep. I see the question.
Hi. Forgive me for not following all of the details, but how much easier would this be if you had a way of saying to the SAT solver, I wish to search all non-isomorphic graphs rather than all graphs?
Yes, I believe it's difficult to say, if not very difficult. The reason being because you need to express a property which essentially is on solutions themselves, right? So you have your SAT solving problem. They generate all possible solutions, but then you would need to say, okay, look through all possible solutions of this part and filter them non-isomorphic ones, which essentially a second order constraint, and which essentially it's very difficult to embed directly. And that's
Yeah, I appreciate the difficulty. I naively attempted to do that and failed a number of times. But I guess what I'm asking is, if we could equip an SMT solver with a theory of non-isomorphic graphs, allow you to say, I have a graph with this many nodes, and then the models will be all of the non-isomorphic graphs. Is that the kind of thing that would be useful?
Well, I believe it would be extremely useful, but I also appreciate the challenges on the way to do it.
Oh yeah, it's hard. I ask because a theory of graphs, and particularly dealing with isomorphisms, is one of those things that sort of comes up about once a year in discussions with SMT people, of big things that only a couple of people have sort of tried, no one's ever really got to work, but hey, wouldn't it be cool if? So yeah, that could be interesting. It's always nice to see people who might actually use it if it was built.
Yes.
Yeah, but I believe essentially what is needed is a kind of second order variant. Maybe QSAT is more appropriate, even though even for QSAT, I don't see immediately how to implement what you are saying in terms of isomorphism checks on the fly, so to speak. Yes.
There have been a couple of papers on techniques like that. I'll see if I can find you some links if that's useful.
Oh, that would be very, very, very much appreciated. Yeah, yes, thank you.
Okay, that seems like a good piece of interaction. I imagine you both know each other's email addresses, but if not, you can put them in the chat. And yes, it would obviously be good to follow that up, because otherwise one ends up reinventing the isomorphism question over and over again. Right. Thanks. Everyone, time for one last question. It's a quick one.